Hello everyone, my name is Wendy. I'm a PhD student at Oxford University. In this study, we did the InSAR analysis to study the geodetic subrate of the Jungarian fault, which is the DZF on the map. It is a large right lateral strike slip fault bounding the slowly moving northern Chia-Hsin in Central Asia, and it has the potential to trigger earthquakes up to magnitude 8, and that's also why we are interested in this fault. During our initial processing, we found that it is a very challenging area for the unwrapping process of the interferograms. This might be due to the slow crustal motion and the high topographic relief up to 3,000 meters in this area. Also, these unwrapping arrows appears mostly as asymmetric or abrupt fringes in the huge basin where alluvial fans and agricultural fields located at. So, we think there is a significant amount of moisture in the basin that makes the unwrapping challenging. In addition, the poorly unwrapped interferograms are mostly across winter or early spring. So, we suggest it is highly related to the snow and the seasonal signals. In order to improve the unwrapping quality, we first do the atmospheric correction on the wrapped face. After the first unwrapping, we did a stacking or the principal component analysis on some well-unwrapped interferograms to extract the seasonal model that depicts the poorly unwrapped area as these red regions show on the maps. We then combine this model with the coherence of each pixel to do the second unwrapping for reducing the unwrapping arrows. And this is an example for the ascending track where the pink large unwrapping arrow is successfully removed with the help in the unwrapping. Before doing the time series inversion, we make sure that the interferograms applied in the inversion are well unwrapped, and we also keep the network well connected in the meantime. Before finalizing the line-of-sight velocities, we use the uncertainty map derived from the linear inversion and the amplitudes of seasonal signals to mask out the bad quality pixels. The red areas on the maps here represent where higher uncertainties or amplitudes are. Also, the high amplitudes indeed mostly appear at the alluvial fans and the range front, or the fields where we found to be poorly unwrapped, which means the seasonal signal do have strong influence on the radar measurements in this area. After removing the high uncertainty and the high amplitude pixels, we got our final line of sight velocity maps. And we made 3 profiles here. We do see the velocities change across the faults for the descending track, which is more sensitive regarding the fault strike and its motion. But the sudden velocity drop in the profile 1 or 2 for the ascending track doesn't seem to be tectonic signals. Those areas are the boundary between the hills and the fans, but we are not sure what is causing this drop yet. Among them, the profile 3 looks most likely to be tectonic signals. So we did a Bayesian inversion on it for the subrate by assuming a vertical fault plane with pure strike slip motion as suggested from the geological observation. It shows the subrate is around 4 to 5 mm per year with a locking depth around 1 to 3 kilometers. In fact, this geodetic subrate we get is higher than the reported geological subrate around 2 mm per year, which is only based on 1 luminescent sample age actually. So, it is possible that the geodetic subrate is closer to the current fault motion. But this relatively shallow locking depth is out of our expectation for this fault that could trigger large slip and large magnitudes with very thick seismogenic layer. So we're guessing maybe the seasonal deformation is much stronger than the local tectonic motion, so that we could not simply define the fault geometry only from InSAR analysis. So for the future work, we'll try to use all the available GPS data as more constraints to decompose the line of sight velocity, and we are seeking more interpretations for these InSAR results. Thank you very much.